So next we have, hang on here, let me get my act together. So we have the first of our two presentations, first group of 6 from Cyclotron Road. Jay Provine, co-founder and CEO of Align Carbon. Sorry, I'm not my act together. I'm not adapting. 2 big barriers to carbon nanotubes for semiconductor applications are CMOS compatibility and the purity. And Jay Provine, I think, has got a solution to both. Welcome, Jay, to Chicago.
Thanks very much.
I told that to work, but let's hope.
Let's see, yeah. All right. Hi, it's great to be here. It's really nice to come from California back to the Midwest, where my wife grew up in Naperville, and we've spent a lot of fun time in Chicago over the years. We're part of the Cyclotron Road program, which is an Activate startup accelerator entrepreneur program based at Lawrence Berkeley Lab. My co-founder, Cara Biesel, and I started Align Carbon about 1.5 years ago, based on work that came out of Philip Wong and Subhashis Mitra's lab at Stanford. She had been in applied materials for several years, and I had been an adjunct professor at the university. We got together to put this company together to really solve a problem of getting manufacturable carbon nanotubes into electronics. And why do you need this? Well, inarguably, the greatest achievement in manufacturing that humanity's ever done is making transistors, right? It's the only thing we make quadrillions of every year. And they're running into a lot of problems. In particular, for high-performance computing, Moore's law is really running into a bottleneck. We'll talk about that more in a bit. But even looking at how we transmit data wirelessly and the big push to have all our cars and phones talk to each other in a much more meaningful way, we're running into bottlenecks for where silicon circuitry can take us and high-power circuitry can take us. And finally, we'd like to leverage these kind of technologies also to do sensing at the molecular scale, right? And there we really need biocompatibility as well as high sensitivity that comes from a circuit. And all of these things really need to be addressed by having high-quality transistors that aren't just made out of silicon anymore. In a matter of taking into account the amount of time, I'm only going to talk about this one going forward, but I think it gives a good example of what we're doing. There we go. So Moore's law, right? Every time you shrink your circuit, it gets better by 100% in terms of energy delay product, how fast it goes, how much power it burns. But that was only really true for the first several decades. And now in the last 10 years, it's really flattened out. Node to node, you only get 10% improvement. But you still spend billions and billions of dollars to shrink these circuits. And this is because the way these circuits work in a system now, the applications are very dense. It's not about making a faster transistor anymore. It's about that pipeline of information from data to compute, back and forth. And that is what we can solve by getting away from our 2D shrinking capability and going to 3D. In order to go to 3D, we can't just have this underlying silicon logic here. I'm not good at pressing this button. There we go. But we need upper layers of logic as well. Additional computing layers that can go above that underlying structure. And that has to be low temperature, or else it messes up the silicon structures underneath. You also need an upper layer memory, right? But that's already in existence. Samsung, Intel, TSMC, they all have upper layer, low temperature memory processes already in pilot production. What no one has is this low temperature, high quality semiconductor layer until we can figure out how to make carbon nanotubes that go into IC foundries. And that's exactly why we started Align Carbon. The nice thing is this isn't just a cartoon on the right. This is something we really built. And there it is. This is a cross-sectional SEM showing 1 million silicon transistors built in Stanford's lab. That corresponds to this layer down here. There's 1 million carbon nanotube transistors. That's that upper layer. There's an RRAM ALD-based layer there in purple. And that was, again, done with ALD and low temperature. And then for good measure, we just put another 1 million carbon nanotube transistors on top to ask as sensors and made this into an artificial nose. Okay, so this is a nice proof of concept, but it ultimately can take us to 1,000x in that energy delay product, right? We're only getting 10% every 2 years out of the shrinking. Now we can go 1,000x so we can build these kind of circuits. Whoops. Going back is just as hard. So we make wafers full of carbon nanotubes. Got one right here. 100 millimeter wafers, got 60 million carbon nanotubes, all perfectly lined, as close as you'll get to a thin film of carbon nanotubes. You can transfer that thin film off onto any substrate. It doesn't have to be a silicon wafer. It could be anything that's reasonably flat. So this exactly is fabricated in the way that gets it into IC manufacturing. It's CMOS compatible. No new tooling is necessary. You do traditional lithography, traditional depth, traditional etch to make your circuits out of this. So the technology building blocks align, right? Now you don't have tubes crossing over each other, interfering with each other, and you don't have density problems. It's uniform across the film. It's like a thin film of carbon nanotubes. Purity. When you make a bunch of carbon nanotubes, single-wall carbon nanotubes, some are metallic, some are semiconducting. For any application you can think of, you really don't want to mix, you want one or the other. And we have a capability that we've patented that is about making either fully metallic or fully semiconducting populations. We have an NSF grant to get us to 4 nines purity semiconductor by the end of this year, and we're on target to do that. And the last thing is that this needs to be manufacturable. And that's CMOS compatibility, but also this low temperature transfer process and everything happening at a very high rate of throughput. It has to go to 100 wafers, 100 substrates an hour to really mean something to the industry. And so we've made sure that all our processes can meet that demand. So the alignment is done, the purity, we're on the way. But we're in good shape on that. Ultimately, we need to take it even higher to get to the top end performance, that 1000x. And the manufacturability is something that we've got a good design principle. We have a manual version of this in place. We want to make an automated version, and that's really why we're out raising. So the nice thing is the IC industry is really well roadmapped. They think about what they want to do for the next several decades. So it's very clear. We're selling stuff right now to major IC manufacturers, and they just know exactly where they want to go, make these milestones, and we'll stop buying it. And the ultimate opportunity is amazing because 250 million wafers are consumed every year for processors. So we think this is a market of at least $5 billion if you can make the next generation of great processors coming on carbon nanotube transistors. So this is what I've been talking about the whole time, but there's another great opportunity in RF space. We use the high linearity of carbon nanotubes, the fact that you can get off of silicon, which is a very absorptive material for RF frequencies. You can go after these high frequency 5G, 6G applications for filtering and other things. This is a smaller market, but it's more quickly realizable, about 400 million. And the nanosensors market, where we've also sold about half of the stuff we sold so far is in biosensing and single molecule sensing. But it's really the Wild West. It's the opposite of the IC industry. No one has a roadmap. They're kind of like build it and see who buys it, which is not a great strategy for a young company. But it has the opportunity to be really big, and we'll see where it goes. Certainly want to keep these customers in case around and happy, but where they're going to go is certainly we don't know yet. So the is really to get those building blocks in place and serve all those industries as a material supplier. And that's a great business. But the vision is to be a customer for our own material and go after everything that we can make with this. Carbon nanotubes can really help all of these industries and really be the next major wave of circuitry-driven materials. And we would like to do that, participate in that both as a material supplier, but because we're the best people to use our own material. So we're out raising around right now to really accelerate the development of all these building blocks, push forward into all of our customer segments. We've got a $2 million round that's half subscribed. We'd love to talk to anybody else who'd be interested. We also like to have people collaborate who think these tubes might be useful for their research. Thank you very much.
Jay Provine. Thanks, sir.